So good morning, Professor, and pleasant good afternoon to all the Indian participants. So warm
Good
good
afternoon.
afternoon. Yeah, warm good afternoon to all of you. So we are here today to listen to Professor Jamal Khatib. So he's a professor, the Faculty of Civil Engineering in Beirut Arab University, Lebanon, and also he's an emeritus professor in University of Wolverhampton, UK. So he's going to deliver a webinar session on biomaterials in construction. I think he's going to focus on the use of biofibers in concrete application. So he has rich experience in the area of sustainable construction materials. So I'm very happy that Professor Jamal Khatib is with us today to share his expertise on biomaterials in construction. So I hope this webinar will be a useful session for all the participants and will get to know about more about biomaterials, use of biomaterials in construction. So with this brief note, let me invite Professor Ruby Freya to introduce Professor Jamal Khatib to the audience.
Thank you, ma'am. I feel honored to introduce Professor Jamal Khatib. So, as ma'am said, at University Lebanon and also Emeritus Professor at the University of Wolverhampton, UK. He is recognized as a chartered engineer by the Institution of Civil Engineers and also the European Engineer. Though his academic career began as a research fellow at the University of Aberdeen, then at South Wales, then he became a lecturer at Sheffield Hallam University. Currently, he is also the honorary professor at Inner Mongolia University of Science and Technology, a visiting professor in University of La Rochelle, France, and Shanghai Jintao University, China. So his areas of research include sustainable construction materials, where he has used waste in the production of construction materials, has used metakaolin in concrete, and research about concrete subjected to harsh environments and light and self-compacting concrete. So he has published many research papers in journals, book sections, and conference proceedings. And his major contribution to the research on metakaolin as a partial substitution of cement has been cited extensively throughout. And he has a huge, a very big research profile. He has been a reviewer for a lot of journals and in the editorial board also. So I welcome you, sir. I hand over the
Thank you very much, Prof. Kumutha, for the nice introduction. Just before I start, please, the whole world is watching the news about the COVID-19 situation in India. So hopefully things will improve in the near future. So all the world is feeling with you. Hopefully things will get better very, very soon. And I hope all your families are safe and well, and hope for the best for everyone. It's not only India, by the way, it's the whole world. But hopefully things will improve with time. So that is the beginning. I thought I'll mention it because it's on the news everywhere. My name is Jamal Khatib. I'm a professor of civil engineering. As Prof. Kumutha said, I'm at BAU at the moment. And I spent actually most of my life in the UK. I decided to return to Lebanon about four years ago. But I'm still Emeritus Professor of the University of Wolverhampton. My other colleagues or the authors are Dr. Masha'a El-Kurdi, Ghanem, and Balbaki. And this is the international seminar. Sorry, I forgot to do the, can you all see the slide view, I guess?
Yeah, yes, Professor.
Okay. This is Professor Kumutha who kindly invited me, and obviously I accepted. But please remember, I didn't have much time to prepare. I wanted to prepare more, of course. And I also wanted to plot the graph in different ways to do comparison. But due to the limited time, I managed to do something there. So, yes. So hopefully I'll be talking up to about half an hour or so. This is me, as Professor Kumutha said. These are my various titles. I've got PhD from Aberdeen. Sorry, I've got my master from Liverpool University, where I still support Liverpool Football Club. Then I went to Scotland, that's Aberdeen, to do my PhD there. It's called the Oil City in Europe. And then following, I managed to get, of course, the chartered engineer status of the Institution of Civil Engineering in the UK. And because of that, I became automatically a European engineer. And in 2016, not a long time ago, I became a fellow of the Institution of Civil Engineering. I'm also a fellow of the Higher Education Academy, although I didn't include it in the titles in here. And I've got various certificates and degrees and so on. In addition to that, as Prof Kumutha mentioned, I'm Emeritus Professor of the University of Wolverhampton, so they still circulate me with the various emails. I'm still to be considered as member of staff, but without pay. And obviously I'll continue to do so. Also, I'm honorary professor. Again, Dr. Kumutha mentioned this. Early in the year 2000, I guess, I became an honorary professor of the Inner Mongolia University of Science and Technology. That is in China. I'm also a visiting professor at the University of La Rochelle in France. I went there for a few weeks in 2015. And as from 2016, I also became visiting professor at Shanghai Jintao University in China. They wanted me to go there and employ me as well, but maybe due to time limitation, I was not able to do so. My previous employment, as mentioned before, while I was doing a PhD at the University of Aberdeen, I became a research fellow while I was finishing my PhD, and I stayed there for 3 years of work and then maybe 3 years of study, so 6 years in Aberdeen. Then having completed the research project, I wanted to look for another job, and I became a research fellow at the University of South Wales. That's not in Australia, by the way, that's in the UK. There is another University of South Wales in Australia. Again, the job was not permanent, it was only contract. They managed to renew it, but I wanted a permanent job. So that's why I went to Sheffield Hallam University and became an assistant professor at that time. And I stayed there for maybe 8 years or so, or 9 years. And then following that, I wanted, obviously, people always look for promotion and so on. So University of Wolverhampton offered the associate professor title. So I went there, and then a few years later, I became full professor of the university. And then when I decided to leave, they gave me the title of Emeritus Professor. These, I mentioned these before, sorry, that is a repetition, just I didn't know this. And one of the climax or the height of my career, to be honest, occurred in October 2020. So it's only a few months ago, where Stanford University ranked all the researchers in the world. And I know there are over 2,000 top ranked researchers in India, by the way. Maybe you should know about it. And I was classified myself as the top 2% researcher globally in building and construction. And I feel, I mean, obviously, I will still be at some point still 2%, but obviously if it happened once, that is really good. And the classification, as I said, was conducted by Stanford University, where they look at different measures actually. It's not only the H index and the Web of Science citation and so on, it's also other things which is combined. It's the age, it's the when you started the work and so on. So it's a complicated equation to work out the ranking. I would like to talk, as Dr. Kumutha mentioned, about using fiber in concrete, and in particular, I wanted to use, obviously, biofiber. Not I wanted to use. I mean, the work in here on biofiber in concrete application. As we all know, concrete has low tensile strength and low ductility, and using fiber traditionally, like steel fiber, glass fiber, polypropylene fiber, can compensate for these negative effects. So instead of having a large crack, for example, we might have more cracks, however, they might be tiny. and also ductility, so the material or the reinforced concrete member will start to give in, and you will see an ample sign of warning before anything happens. But I mean, generally, with the use of fiber, we got an improvement in bending and tensile strength. We've got greater resistance to cracking and better ductility. That's fiber in general, whether they are synthetic fiber or natural fiber. Now, not recently, in the last, say, 10 years or more or whatever, people are keen to preserve the environment, especially in populated area. And obviously, this is really directly relevant to places like India and so on, where you've got large population. You need to construct more houses, and you need to be more sustainable. You cannot say use virgin material all the time, because the virgin material or the quarried material are limited. So if we can save material, that would be okay. If we can use also local material, that would be okay, because that would reduce the need for transport. And also, if you also use material that requires low processing stays cost or processing time, that is also will be good. But if we talk about biomaterial in general, and natural fiber is part of it, that obviously this is sustainable, because plant they are reproduced all the time. So if you use the leaf or the stem, they can regenerate. So even if we take the whole plant, we can always plant something else in there. And it's not only this, people say this is considered to be zero carbon, because if you use energy or burn or whatever, then the new plant will suck or will absorb the CO2 from the atmosphere and reduce the carbon dioxide emissions. So it's topical, it's trendy, and that's how the future, we think, will evolve, and we're going to use more material like this. But however, of course, there are problems, and major problems, either whether it's engineering properties, or whether absorption, whether it's durability with time, and what to do about it. I'm going to focus in my work on found palm fiber, where we did quite a bit of work in the last 4 or 5 years. Also, in the last 2 years, we started to use another plant called Australis phragmitis fiber. Australis phragmitis, and we obviously extracted fiber from there. On this occasion, it's from the stem. Because the reason being that they are locally available. I wanted to do research relevant to maybe Lebanon in our case, where this material is available, and actually it's causing problem for farmers to get rid of it. Apart from burning, they can get rid of it by burning it. And obviously, burning is not a sustainable option. If everyone wants to burn, it's a problem. So that's how palm fiber, I'm sure you've got plenty of it in India. We managed to extract, of course, fiber from the leaf in there. So you cut it, we've got a machine, and to extract the fiber in whatever shape and length we want. This is the Australis or Phragmitis australis plant in there. It's like little bamboo, I think, or cane or whatever, fairly similar, but a little bit smaller. So it can grow bigger. So that is a human being, say that. Suppose that is 1 meter and 70 centimeters. So it can go over 3.5 meters. And of course, in wetland area, that causes problem to the farmer, as I indicated earlier. So if we can use it in a useful application other than burning, that will be actually useful. The objectives of our work, we did work on palm fiber, and we did work on Phragmitis australis. So we use these as fiber inside concrete, and we looked mainly at mechanical properties in this case, like strength UPV. We looked at durability related properties such as absorption, total absorption, capillarity, and so on. And we are doing lots of work on durability. So we will be doing more work on durability, also the effect of treatment. I might mention something like this in here, but it's not the purpose of this particular presentation. The reason we do treatment, of course, to improve certain properties, to make the actual fiber last longer, because it's an organic material, and we don't want this material to degrade with time. And this is really very, very crucial, and more research should be focused on this. And we're hoping that, obviously, if we consider the region where I live in, if we use, if we manage to be successful in our research, this hopefully will pave the way for more utilization of natural material, and that this is directly, obviously, linked to sustainable construction. And much of, or more people now are talking about United Nations sustainability goals, and I believe this can fall within this category, and every one of us should do his or her role in achieving this. Remember where I live now in Lebanon, I was in the UK there, and you are in India. I think if you look at the top populated nations in the world, UK is quite populated, Lebanon is quite populated, India is quite populated. So I believe this type of research will be useful. This is, I don't know how to get rid of the screen share in here, so stop sharing whatever icon there, but it doesn't matter. I'm not going to do anything in case something goes wrong. So we managed to get fiber from palm, and these are the dimensions. So we have a length of, say, something like 3 centimeters or 30 millimeter. This is the thickness, very, very small, and I don't want to say it's really 0.25. It could be 0.23 or 0.26 because it's very, very thin. It's a leaf. And then a width of 0.6, that's the one we used in our work. But the width varied between 0.6 and 0.9, and the thickness varied between 0.25 and 0.35. We believe that's about right. So it's less than half of a millimeter. The width is this, and also these are the characteristic absorption, modulus of elasticity. We did take one fiber and we tested on a small machine to get these properties. We tried to do it on the Phragmites australis, of course, but I don't have the results with me in here. For the Phragmites australis, we used a length of 40 millimeter, which is slightly different from the one before, and a width of 2 millimeter. And that is one thing in our research. I mean, in the future, we're going to focus on comparing like with like, but at the moment, we did 2 separate investigations. We didn't do them together. So that's why I'm reporting each one at a time, because we cannot compare, to be honest. Otherwise, it has to be the same mixed proportion, the same length, same aspect ratio, and so on. But nevertheless, this is the one we managed to do in our work. So the width is 2 millimeter, 40 millimeter length, bulk density of 665. And obviously, in this case, we try to treat it with NaOH solution for 24 hours. That's the simplest type of treatment. You leave it at room temperature or lab temperature. And of course, there are different ways of treating the fiber. Some of them, they use heat and so on, but we want it to be as environmentally friendly as possible. So we use normal environment, and we sort it for 24 hours. And obviously, the purpose of the treatment, it will have various, couple of main benefits. One is the alkali is slightly reduced in the system. Degradation time will be less, because that will be, as a material, it will be more durable. And also, although we haven't done much work on it, the surface of the fiber will get rougher, and if it's rougher, that will increase the bond between the fiber and the concrete matrix. So you have 2 benefits. And then after this treatment, of course, we wash them again with water, then dry them. And once they are dried and reach a constant weight, then we store them in polythene bag ready to be used. Straightforward for the results. Remember, I'm reporting now the work on palm fiber only. As we increase, and you will see later in the second slide, in general, the progression or the development of compressive strength with time is pretty much similar to any traditional concrete. So there is nothing really different about normal concrete and concrete with fiber. Yes, the values are different, higher for the 0%, that is the normal concrete. As we increase the fiber, the strength is going less. Remember, on some occasion, we get an increase, but it depends what the biggest design we have and the water to cement ratio. But partly because this has lower density and the strength is lower. So that is the only justification. Maybe there is something else, maybe more porosity within the fiber or more pores, but we will see the results on water absorption there. But there might be isolated pores which might reduce the compressive strength. So there is the issue of density and the pores within the matrix when we cast concrete with fiber, because visually, although we cast them, we compact them very well, but there is always this gap between the fiber and the matrix, which can create pores. If we want to look at the percentage reduction in compressive strength with the increase in fiber, and we can see up to, say, 30%, 35% reduction. And the more fiber we have at later ages, the more reduction in strength we have. But earlier on, 3 days, 1 day, sometimes the results are not too clear. We cannot rely on them too much. But the long term, you can see, for example, the 0.5 and the 1%, they give or they yield similar results. Not at 7 days, though. But in the long term, if we focus on this, the higher the fiber content, the lesser the strength. But between 0.5 and 1, in here there is not too much difference, but at 7 days there is much difference. Sometimes difficult to explain why it happens at 28 and 90 days, but not at 7 days. Looking at the dry density of concrete with palm fiber, and because the density of the fiber is less, is 600-700, as you noticed earlier. Of course, if we include them in concrete, and if we increase the amount, the density is going to get less. But it's not really drastically huge in density. It's 2276 to 2190, but there is a slight reduction nevertheless. And with time, I would say it's about the same. Maybe later on they became the same with no obvious reason. And here, obviously, they get reduced as we go along. But as in general, there is a reduction in density. Please remember one thing: we try to explain the results, why they are the same, why they are not the same. Again, it's maybe to do with the compaction method, which will yield less density and also creation of pore inside. So it might happen in here more than the other. Maybe we need to put a section throughout the specimen and observe it via SCM to look at the difference when we increase the amount of fiber. Ultrasonic pulse velocity, as you can see, it's closely related to compressive strength. The higher the strength, the higher the pulse velocity. The lower, obviously, the lower the pulse velocity, but it's to a lower extent. You can see it more in compressive strength. You can see more reduction as we increase the fiber content. But in here as well, you can see reduction. The control is higher than other concrete. The control has higher UPV than other mixes. And in here, there is more or less a continuous decrease as we increase the fiber content. It's pretty much the same at 28 days and the 7 days as well. So whatever we do, now, total water absorption. We did, obviously, we did various tests, and I'm reporting what I managed to find, of course. Total water absorption, we also did water absorption by capillary action. As we increase, generally, apart from the 0.5 fiber, which is this one in here at 7 days of curing. So this is 3 days, 7 days, 28 days, and 90 days. I'm sorry, the number of days are hidden below this. I don't know that I can. I think I can move it. I didn't know this. So, right. Okay. 3 days, 7 days, 28 and 90 days. And of course, lower water absorption, technically, we should get more strength. And we try to explain the results. Maybe we have isolated pore and these will not maybe appear when we do the total water absorption. So that is one thing maybe in the future where we might do, look at it closely and do SEM studies on various specimens and see how they vary. If we've got more isolated pore, we cannot obviously measure them using the water absorption because there is no open channel to get into the pore. So that is a possible explanation. So I'm not really, as I said, we might repeat some of this work again in the future. But generally, the general trend, slight reduction in water absorption, but it's not huge. I'm sorry, can you still hear me? For some, that's it. Okay. Capillary water absorption. So what we did, we subjected one face of the specimen into contact with water, and we monitored the amount of water being absorbed and with time. And then we plot the water absorbed versus the square root of time, and the initial slope of the curve is referred to as the capillary water absorption test. It's a simple test we do, and my earlier paper got many citations. That was back in the mid-90s and so on. Well, it's a simple test, and sometimes you can relate it to SEM results, to MIP results, that's mercury intrusion porosimetry, and so on. So it's a simple test, but yet it's effective. As you increase in here, what we have seen, the higher the amount of fiber in the system, the higher the water absorption coefficient. So basically, the water absorption by capillary action is more when we use fiber. So the higher the fiber content, the higher the water uptake by capillary action. So that is obviously an indication of the open pore and the open pore size and so on. Maybe we think it's because of the presence of fiber. It can act as a bridge for the water to go through onto the sample there. But why it didn't happen, of course, in the total water absorption, it's quite interesting to compare the results. Remember, capillary water absorption, it's via capillary action. The other one is total. So they are not exactly the same. I think they are related, but they are not exactly the same. And if we look at percentage in percentage term, it's quite clear in here that as we increase the amount of fiber in the system or in the mix, we have an increase in capillary water absorption. And this is, I mean, this increase can be over 100% in 90 days, and it can be 100. So there is a substantial increase, and it's quite obvious. Sometimes it doesn't happen at all ages. Maybe we think because of experimental error and so on. And of course, the capillary water absorption test is quite sensitive. We try to remove the sample each time, then put it back, and you need to dry the sample. You have to be very consistent in the way you do things. And if we look at correlation now, remember I'm talking about palm fiber in here completely. So correlation between strength and UPV, the higher the UPV, the higher the strength. We try to do it at each age, and there is some sort of relationship. But if you look at the whole results in here, to be honest, let's face it, we can make a best fit curve or best fit line for all these results. And again, as the compressive strength increases, the ultrasonic pulse velocity increases. And there is some sort of linear relationship for these results. In my previous paper, in the paper which were highly cited, I think we correlated them via exponential relationship, e to the power, and then that gave a better prediction of the results. But at the moment, linear seems to be reasonable in here, but if you consider the whole lot, it might be exponential. This is also correlating compressive strength with capillary water absorption. As the compressive strength decreases, the capillary water absorption increases. So that's quite obvious. So if you've got more flow for the water to come in, then that will adversely affect the compressive strength. But there is quite nice relationship, and we tried to do each age at a time, and there is some sort of a clear relationship there. We can combine all the relation, but they don't give you on this occasion some sort of correlation, good correlation. Now, moving to Phragmites australis. So what I've reported so far was the palm fiber results. In here, I'm going to report the Phragmites australis results. Density, quite clear. Obviously, we tried to excel with the test now. There's quite clear reduction with density or in density as the percentage of fiber increases. And to be honest, it's pretty much similar to the results for palm fiber. The reason I didn't put them next to each other because the design of mix of are different, so we cannot simply compare them. But what we can say, there is reduction in density as the fiber content increases. Slump, we've got reduction in slump as we increase the fiber. And again, we try to be honest in the way we report the results. This is not consistent in here. Whether it will happen again, I'm not really sure. It's slightly not, it doesn't follow the trend of the other results. We are expecting it to be somewhere in here, but to be honest, we try to report, we want to be honest in the way we report things. Sometimes certain things happen in the mix without knowing them. But generally, as the fiber content, Phragmites australis fiber content increases, the slump decreases. And in terms of compressive strength as well, in the previous one, we noticed quite an obvious reduction in compressive strength. In here, actually, we don't see much of reduction in strength in comparison. Only at day 3, and then at 28 days time. So just 2 seconds, please. I'm really sorry. I've heard a bit of noise in the background, so I wanted to close. Because we're all doing things online now, so I'm really sorry. So as you can see, the distinct difference between this type of fiber and the other type of fiber is we didn't have much reduction in compressive strength, and the reason being the fiber in here are quite thick in there as well. We did work on split tensile strength, and you can see there is a slight increase with the increase in fiber at early ages, 7 days. But at 28 days, to be honest, the tensile strength did not increase as much. Although it's up and down, but actually the variation is not that huge. Total water absorption, again, this is on Phragmites australis. So the good thing about it, it's slightly different behavior in here. Maybe the type of fiber we're using, and we've used the stem from the Phragmites australis plant. The stem tend to be like bamboo. It can be strong as well. So it can. We've got reduction in total water absorption, and it's quite obvious actually. So it's not exactly the same as the one for palm fiber. So there is a distinct difference between these two, and this is actually some of these results, please, are under consideration in one journal. And sorptivity index, pretty much similar. The higher the fiber content, the less the sorptivity. Sorptivity, that's exactly the same as capillary water absorption, same trend. Whether we call it capillary water absorption or sorptivity index, they're pretty much the same. In one of them, like the one in here, we we use one equation where the row of water is being used or the density of water, but they are pretty much the same. So if whether we use capillary water absorption or sorptivity, the results are pretty much the same. In general, let's look at this, and whatever applies to palm fiber, it applies to generally it applies to Phragmites australis fiber. So it was found that if we use 1.5% volume of fiber, we've got up to 35% reductions at 7 days. So maybe we need to focus, rather than focusing at 7 days, we need to focus at 28 days. Density, there is a small reduction because the higher the amount of fiber, the less the density. And of course, the UPV data they follow pretty much similar trend to those of compressive strength. Total water absorption indicate that FRP was not the main factor affecting concrete absorption. On the other side, the effect of curing age on absorption was significant. So if you look at the water absorption at early age, is not the same as the one at later age. Again, I want to stress the point on proper compaction. Although you compact them very well, but inside it's very difficult to assess whether they are compacted properly. On the surface, they appear okay. So maybe that's why we're keen to do some SEM studies on different surfaces to compare. And again, in here, there is obviously straightforward relationship or correlation between capillary water absorption and the amount of fiber used. And there is obviously, as you see from there, compressive strength and UPV are strongly correlated. And we assume there is linear relationship at each curing age. And also, if you look at strength and capillary water absorption coefficient, there is also some sort of a linear relationship. If you combine the whole results, the relationship would be different. So we think that using fiber up to 1% doesn't have any negative effect. We need to do more work on ductility. We need to do more work on durability. We need to do more work on crack propagation and reinforced concrete beam. So financial support of BAU is gratefully acknowledged. And with that, I like to conclude my presentation, please. I'm not sure with the time. Maybe I said half an hour, was I? Thank you very much for listening.
Thank you, Professor. And the participants, if you have any questions, raise the questions to Professor Jamal.
My pleasure. Yeah, thank you. Prof. Kumutha, if you recorded the lecture, if you would send me the link later, that would be kind of you.
Yeah, definitely, Professor. I'll send the link to you, the recorded session. Yeah.
When it's finished. And if there is no question, obviously, thank you very much for inviting me, and hopefully we can collaborate in the future on the research front when things improve. And if you've got any idea, please let me know.
Yeah, definitely, Professor. So any questions from the participants? Yes, Ruby, who is going to propose vote of thanks? Can you call Vivedita Varshini?
Yes, Vivedita Varshini.
Yes, ma'am. Respected and most distinguished chief guest of the day, Professor Jamal Khatib, our beloved HOD, Professor Kumada, other honorable professors, and my dear friends, it's my privilege to have been asked to propose a vote of thanks on the seminar event. I, on behalf of the entire fraternity of Civil Department here, extend a very hearty gratitude for Professor Jamal Khatib for gracing your crucial work and sharing with us your opinion today. Thank you, sir, for your very thought-provoking and interesting address. I'd also thank our beloved HOD for her guidance and moral support. I'm happy to express a vote of thanks to our staff that has made this seminar a grand success through their motivation and dedication. I'd like to give my vote of thanking to the coordinators of all the events for making the seminar a great success. We are also grateful to the entire department for organizing this event in such hard time. Finally, I thank the wonderful students who have turned up in such great numbers, not only from our department, rather also from other departments of the institution. Thank you so much for your cooperation. Once again, I thank all for your cordial cooperation. Thank you.
Thank you so much for the nice words.
Yeah. So in this occasion, I'd like to thank Professor Osama also, because through Professor Osama only I've got connected with Professor Jamal Khatib. Yeah. So convey my regards to Professor.
Yes, I tried to invite Dr. Osama, but I couldn't find his number on my set in here. It was in the other phone. Okay. So I'm really sorry, but maybe you could send him the link of the PowerPoint presentation.
Yeah,
if you don't mind. When you send it to me, I'll send it to him. But yes, he's my colleague, and we're happy with this collaboration.
Yeah, convey my regards to Professor Osama also. Thank you, Professor.
Yes, he's from the architecture department. Yes, thank you very much.
Yeah, thank you, Professor. Thank you.
Yeah, all the best. Bye.
Yeah, thank you so much.